Good afternoon to everyone. And after we heard about this nice lecture about black holes, now we come back on something that is larger, way less compact, and perhaps might be dark matter. So let's come back from where we started last time. So in the first lecture, with perhaps an historical cut, I tried to make the case that dark matter should be there. And not only should be there are a lot of candidates for it. And as we already heard between today and yesterday, and 2 days ago, this can be made of scalars. And as you see, scalars are often coming back in all the fields of gravity, and not only gravity, it's a standard model and so on and so forth. So it's probably worth to have a look at scalar structure from a generical perspective, because it might not be dark matter, but it might still be there, or might be a proxy for something that is slightly different, or might be just a part of the cosmic abundance of dark matter, or whatever other particle. So it's kind of a generic motivation, but it gives you an idea of why the field is increasing exponentially. Not the scalar, our field. So this was the kind of outline that I left last time on the thing that we are going to explore. And this time there is going to be way more equation. I'll try to put there some passages, not all of them, but the idea would be, let's take a scalar structure, let's perturb it, let's look at the modes, let's put some kind of perturber inside, so it's a binary, a particle that is plunging, a particle that is oscillating between one side and the other of the halo. And why this might be important, precisely this example of a particle moving or oscillating. Because there was an argument by Bekenstein some years ago that shows that when you have gravitational collapse and it's not perfectly spherical, there might be the emission of momentum on some sides, on some direction, a linear momentum. So by conservation of energy, black holes that are formed by gravitational collapse might move. And the typical velocity for these kicks is around 200-300 kilometers per second. So I think I had this on the last slide of yesterday. Some of these black holes might escape the galaxy. And not only the product of gravitational collapse, because there are super kicks that comes in when you have a binary that is colliding, that is spiraling, and you have production of a black hole, and actually these kicks can be 1,000, 2,000 kilometers per second. So if you have a black hole moving in a medium, because actually it's moving for other reason, not because there is dark matter, well, then it might interact. And this kind of collective feature of having dark matter particles all around might be still important. On the other side, how to compute that? Because now we don't have a collection of particles. You have one object with a typical de Broglie wavelength that is large. So the effect of the potential well that this dark matter halo is having on the particle, and the fact that all the scalar is behaving as a wave, means that you should take into account the entire structure, and therefore solving the equation for the perturbation induced by a perturber, that it might be your black hole, inside the scalar environment. Said that, we need an ingredient. And there was a question, I think it was from Marco Aurelio the other day, about the massless, using massless scalar field. And we use massive scalar field, even if the massive scalar field is very small, because we need a kind of potential well that traps the scalar in forming an object. If you don't have that mass, it will just disperse and not keeping itself together. There is, though, an example that I spent some time working on it, but it was published only as an appendix. They are called cuboles, that were, I think, already mentioned by Eugene as solitons, that have a non-trivial time dependence, and not only have that, but also have a potential that is something like 5 to the second, 5 to the fourth, 5 to the sixth. And this basically gives you that there might be a non-trivial solution, solitonic solution for this nonlinear scalar that doesn't really need gravity to be bounded. But the reason why there are this kind of solution and they are kept together is because of a non-trivial potential higher order to the one that we are only considering here. That is 5 to the second. So 5 squared, but we have a massive scalar field. So that's why we can construct object made of this light scalar. So basically, the first thing is that we are violating the Derrick's theorem because we are looking at time-dependent solution. Otherwise, there will be no time-independent solution that will be stable and therefore a good candidate. It's true that stable always has to be accompanied to the time scale of the instability. Actually, that's an important point. If you look at the theory that I'm going to show you, not for a complex scalar field, that is one that I use, but you use a real scalar field, you can create this scalar object called oscillatons that might be something like these boson stars, but they are unstable. But they are unstable on basically a very, very long time. So these oscillatons might exist, they are actually stable in the time in which they exist, but you know that after a certain period of time, they will just disappear. So it's probably worth to have a look at the same kind of method that I'm going to apply here for this real scalar field. But I'm not aware if there are already calculations. Correct me if I'm wrong. But for now, we're going to look at a complex scalar field. So the theory is GR. Then we are adding a complex scalar field phi with this mass mu, well, quantity related to the mass mu. This is going to be around 10 to the minus 20, 10 to the minus 21 electron volt, but it might be even 10 to the minus 18, 19, okay? That's more or less fine. We're still modeling dark matter halos with these kind of small masses. The scalar field stress energy tensor is gonna be that T mu nu there. And then if you vary this action, what you are gonna have is an equation that is your Einstein equation. And on the other side, you will have the Klein-Gordon equation. Now the Klein-Gordon will have this phi mu square term, and the Einstein equation will have the source of the scalar field, where I'm putting here basically what? The fact that this is, as Eugene was saying, a U1 global invariant theory, so what happens is that you have another charge, and therefore you have a current that is going to be conserved. And what you can do is associate the number of particles and the energy of your configuration that is basically given by this integral, where you're integrating over a constant hypersurface of constant time. And what you integrate is the time part of the current. This gives you the number of particles that you have. This is important because when you have a structure and you perturb it, what is happening is that we say, okay, we are seeing a black hole that is slowing down. Well, but when the black hole is interacting with the environment, it's sending particles away. But it's slowing down eventually, or accelerating, depending on your dynamics. But it's going to transfer also some energy to the medium where it lives. So you need to have an argument that I hope I'm going to show you at the end of this lecture or at the beginning of the next one, to show that for this kind of theory, for this kind of matter in GR, where you have another charge, the number of particles that you are sending away is matching precisely the number of particles that your medium is losing. So there is no creation of particle, and that's fundamental because in this way we can relate radiated quantities that are the one that are the end point of your integration, numerical integration, with quantities that refer to how is the motion of your object. So you can say, well, your black hole actually lost this energy. This energy went a bit in the environment and a bit in the radiated energy, but the one inside the environment is actually a kind proportional to the one radiated. So in the end, you will have only one expression for the momentum lost by a black hole and the energy that an observer measured far away. And that's important because that's going to be our definition of dynamical friction. That is not precisely the definition that Chandrasekhar or Steiger gave, in which you relate the force that the environment does to a single perturber. But our definition is going to be, okay, we had a dynamical event, something happened, the black hole moved, how much is slowed down? That's still an indication, if it's slowed down, depending on the sign, that's still an indication of what happens inside these dynamics. What you're going to do now, when you have your oscillatons, your boson star, your Proca field, and this is something actually that is an open field because there are no Proca solution for the Newtonian limit, so it's something that if someone want to look at, it's worth, I think. What you're going to do is start from your equation. You will still have Einstein-Klein-Gordon, clearly. But there is a very nice feature that if you say, I'm interested in dark matter, I'm interested in objects whose compactness is small. And for small, I mean that in some geometrical units, the mass to radius ratio is around 10 to the minus 5. So you can prescribe a metric function that is basically the first post-Newtonian expansion in the in the post-Newtonian expansion, you can only consider the Newtonian term. That's the main point. So what you say is that your GTT is going to be -1, -2, u, when u is the Newtonian potential of the object. And for the one that are not familiar with the post-Newtonian, this is just a way to parameterize the curvature of an object in power of the Newtonian potential that it would have as in Newtonian theory. So this is an important point. Regardless of the calculation of the equation, it's an important point. We are constructing an object that is an approximate object, because we are saying that the metric is only valid up to this order, and with this order I mean that u, the potential, is order epsilon square with epsilon bookkeeping parameter. That if you want to be actually more formal, that's basically c to the -2. So u is c to the -2. You could do all your game with c to the -2, as in the gravity book by Willem Poisson they do. Why I'm writing here epsilon instead of c? On top of a perturbation, because this guy, this Newtonian boson star, is going to be a perturbative solution of the Einstein-Klein-Gordon equation, we're going to perturb that object. And to be sure that the perturbation live between the Newtonian term and the terms epsilon 4 that I'm canceling here, you need to introduce a new scale that you can call an epsilon 2. You can call zeta. I think we call it zeta. And be sure that your perturbation lives between the first post-Newtonian correction to your background and the very same background that you used. So we check that. Yeah, I think it's not going to be in the slide because the calculations were too long. But if you want to look at the entire calculation, we can talk later. So what we start with is these ansatz, GTT, Newtonian potential. You can calculate your Ricci tensor. And assuming that the background is Newtonian, and assuming that it's non-relativistic, what is going to happen is that your time derivative is going to bring down a 1 over c, and you can basically cancel some terms like derivative of u. Well, but the object is made by scalar, so also the scalar itself will have some kind of ansatz to be non-relativistic and Newtonian. So if you do a rigorous expansion in 1 over c, what you can show is basically that the derivative of the scalar field, the special derivative, are order epsilon square, while the time derivative are order epsilon to the third. And what I wrote here is basically that your scalar field has a time harmonic dependence where mu is the mass of the scalar field. How to look at this? Why these holds? Think about that the scalar field has to be non-relativistic, so the energy of the scalar is going to be dominated by the rest mass. So in an expansion of mass plus momentum plus the fact that it lives in a bounded object, so there is the Newtonian potential of the object, this term mu dominates compared to the other. And when you plug this inside here, because you can imagine the scalar field is, from a quantum mechanics point of view, e to the minus et, what is happening is that every time you derivate, all the derivatives will bring down a 1 over c, and the only thing that matters in the end is going to be this mu. So if you plug these ansatz that are your starting point for both the Newtonian potential and the scalar field, that are the two dynamical quantities that will define our Newtonian boson star, what is going to come out is that you can write your stress energy tensor for the scalar at leading order as this nice term 1 half mu phi square. And now your Einstein equation, if I come back 1 second, sorry, remember that this Ricci tensor is just this operator times u. What is going to happen is that your Einstein equation will become this very nice simple equation where you can see that the Newtonian potential is sourced by the scalar field. Applying the very same formalism, your Klein-Gordon equation will be just a Schrödinger equation. That will have this form in which you can see now there is a coupling between this scalar field and the potential. So the scalar field source the potential and vice versa. And this is called the Schrödinger-Poisson system. So sometimes I write SP instead of EKG. This means Schrödinger-Poisson. And this has like a countless of other uses, even in cosmology. So this kind of computation, starting from one and going to the other, from Einstein-Gordon to Schrödinger-Poisson, might be useful even in other fields, not only in this case. What I'm hiding here, all the part of the perturbation that I told you before. I told you because in paper it was like 10 pages, so it might have been a bit too long to put it here and have a lecture of 1 hour. But the idea would be that at this point, instead of considering only you add the other terms, you do the very same thing for phi, and what is happening is that you're going to have that your system, Schrödinger-Poisson, now will be a function of delta phi and delta u, because you want to know the perturbation to the Newtonian boson stars, and you have to be sure that this perturbation lives between the zero order Newtonian and the first post-Newtonian correction. If you do all the calculation, I will show you where you will arrive. It's a relatively simple system of equations. So it's basically a Schrödinger-Poisson at first order in the perturbations. And what you can do there, you can also add a particle, or you can add a binary. So what you do in general is, I take my Einstein equation. On the right side, I will have T mu nu from the scalar, plus a T mu nu from the particle, or from whatever object you want, point-like. And that's fine, because the size of this object is very big. So eventually the scale of what you're putting inside doesn't really matter. And what you're going to have is a system of equation for the perturbation induced by an external object that live within a Newtonian boson star. I bet the system for Oscillaton is precisely almost the same, and for Proca field might have some equation more, but some can simplify. So the physics should be in these passages. There should be nothing more shady. Is there a question or there questions up to now? If not, we have to solve this system, right? So now we have this nice Schrödinger-Poisson system. We want the solution. And what we are going to impose is that this scalar field, 0, because it's the background. Imagine that we are going to do perturbation later. So this is at 0 order. Yeah, he's going to have this time dependence where omega capital, it's general. I put it like this because we were doing different objects. So for the cue ball, it's the same ansatz. But what you are really doing to obtain Newtonian boson star is write this capital omega as the mass of the scalar field minus a value, that this value, gamma, is going to be found numerical. But gamma still has to be way smaller than mu. So basically, the entire eigenstate of energy for the scalar field is dominated by the rest mass, mu. You will impose your nice boundary conditions, so somehow you want your scalar field to be bounded. At infinity, you don't want scalar field to grow. You want to be asymptotically flat. And also, you can impose a condition on the derivative. And, well, you're going to find Newtonian self-gravitating solutions. In general, inside your Einstein equation, you could place a very complicated potential. But here we are only interested in this mass mu square, and I was telling you what you will find at Newtonian boson star with these small compactnesses. And this is actually the endpoint of the integration to find the solution. So this is the background that we're going to perturb. The scalar field in some normalized units, and this is the corresponding Newtonian potential. So here there are two things that I want to highlight. The first refers to the first lecture. There are no cusps. the density of scalar, when you go towards the center of the halo, is not increasing. It's 1 over r, as the n-body simulation using WIMPs are actually suggesting. So that's already a good thing for this model. And the second, it's gonna be shown mathematically in the next slide. That is unus pro omnibus, omnes pro uno. So I do only one integration. I find this profile, and this profile is the same for any Newtonian boson star, because all the quantities entering the Schrödinger-Poisson system scale in this way. So you have your scalar field, your potential, and the value gamma that I was telling you before. You can rescale them introducing a parameter lambda, and if you rescale at the same time the radial component of these spherically symmetric Newtonian boson stars, what is going to happen is that the mass will scale like this. So you will find a new Newtonian boson star with a different mass. So if you find one, you find your parameter gamma is, if I remember correct, was 0.69, and I was like, okay, but why? And then we were looking at the paper, I think it was Guzman and Ureña Lopez, and they had this nice property, and then, okay, we were like, okay, it doesn't really matter because we can just rescale all the quantities. And that's also nice, because sometimes numerically, when you do perturbation, you are interested in a certain regime. But maybe the regime that you are interested for the physical number that you want to then compare with nature were very small or very big. But that doesn't really count, because we can do the calculation for numerical quantities that are suitable for our code, and then rescale the results, because everything rescales actually. And it will also rescale in the perturbative system that I didn't show you, and I will show you next. So you can find a very similar relation between all the quantities, and even the perturbation are rescaled. So you do one calculation, and you have all the family of zero-node Newtonian boson stars, because these are fundamental. There are no nodes for the scalar field, but eventually, if you change that parameter gamma that I was mentioning, you will find other solutions that have more nodes that, in some sense, are always called the excited states. We look only at the fundamental, but the physics of the results should be more or less the same. A typical value for the mass, actually no, that's even better. Since everything rescale, and the radius rescale, and the mass rescale with this quantity lambda, you can find the generic expression for the mass with respect to its radius, and here I'm normalizing to the mass of the scalar field of 10 to the minus 22. So basically this tells you, this law tells you that 98% of the mass, because these guys don't have a surface, right? A definite surface or an hard surface, is included as a value, or roughly 10 to the 10 solar masses inside 100 parsec. Then you can, if you want a larger or smaller Newtonian boson stars, if you make it larger, the mass will change accordingly to this law. And these actually also contain a number of particles that is, I was mentioning at the beginning, is this Q that is associated with the integral of the stress energy tensor 0, component of the scalar, that actually at this leading order is just pi square with some factor. And it gives you this nice idea that the mass of Newtonian boson stars is, as you can expect, the product between the mass of each particle and how many particles there are. Not very surprising, but still a consistency check somehow. So now when you have this kind of objects, you want to perturb them, because you want to see if they are alive. Something happened, you move them, they explode. And in general, even if the object that you are studying is spherically symmetric, the most generic perturbation, that's why the psi 0 before, is going to have this form with all the coordinates inside this game. And even the Newtonian potential now will be perturbed. And that's perhaps comes back to the question that Carlos asked the first day. When you perturb them, you are also inducing a perturbation in delta U. That's why you will have this emission of waves, even if this system actually don't have this gravitational wave, gravitational cooling as boson stars, as compact boson stars have. This is the system that I was mentioning before. So this is the linearized Schrödinger-Poisson system in which the protagonists of the game are the perturbation, delta psi and delta u. And as you see, these terms is linear in delta psi and delta u, and has terms as product of psi 0 and delta psi. So the background multiplies your perturbation, and this p is a generic quantity that is related with the particles that you put inside the game. So if a perturbation is actually responsible, if a perturbator is actually responsible for the perturbation, you can model it in this way. And here I'm taking just an external point like perturber, but you can do a sum of two, and they will actually be a binary. Why you are interested in these guys, in having the perturbation? Because you can relate delta psi with the radiated quantity that actually are telling you what happened inside there. So you can write, for instance, if you have a circular motion, so an object that is two objects moving inside, the circular, or one object in an emery, so imagine you put a central black hole inside the halo, and you have another friend that is going around. This is going around forever. We don't have radiation reaction in this kind of system. And what you can write is an average energy emitted every period. So you have the E dot, so how much energy is emitted per unit of time. You have the P, so the linear and angular momentum L, emitted per unit of time, and how many particles are emitted per unit of time. If instead you have a finite time interaction, so you have an object that is plunging, what you will define is a spectrum. So it's something like the derivative of the energy with respect to the frequency. So you see how much each frequency is excited during the process. While in the other case, for circular motion, you will have an average of time. That's why you have the E dot. Normally, when you have a Klein-Gordon equation, we are more used to look at an ansatz for the scalar field. Okay, my head will cover it perfectly. That is basically this guy. So you write that the scalar field, the sum over all the harmonics with these L and M numbers, your spherical harmonics, a function that you need to solve for, that we call Z1, multiplying this harmonic time. Well, if you plug this inside the Schrödinger-Poisson system, it will not decouple them. To decouple them, you need another function, a generic function, Z2, that will still have its dependence on the frequencies and the spherical harmonic indexes L and M. In general, that is independent from Z1. For a system like ours, in which there was that U1 invariance that I was mentioning in the beginning, one is actually proportional to the other, which I think it's minus the conjugate part elevated to minus 1 to the m, the conjugate part of the other. But still, generically, these ansatz might be good when you are not really able to solve your system in the usual ways. And in fact, what you can show is that the Schrödinger-Poisson perturbative system goes to this simple equation. So now we have the derivative of a vector minus a matrix times the vector himself equal to another matrix, where the matrix is given by now a generic matrix that contains the potential. So it is a matricial generalization of the effective potential that you find for the Zerilli equation, that you find the geodesic equation where they are separable. Now we contain the frequency, the mass of the scalar field, the background, and this vector x, that is your incognita vector, will contain the solution for the scalar, so Z1 and Z2, the function you need to solve for, and U, small u, it's basically when you decompose the potential, like delta U capital, it's equal to the same guy, but instead of Z1 and Z2, you use U and U conjugate. And normally these potential perturbations are real, so that's why you don't have two functions for that guy. So now you have a vector you need to solve for. No problem. You will solve for it. And now there is one caveat that is I didn't put, because I didn't put all the equation for the perturbation, but you can imagine the following thing happening. I am putting a particle inside something that has to be Newtonian and not relativistic. This particle might source relativistic or non-relativistic perturbation. And this can happen because the scalar field can be very small. So it can also source ultra-relativistic perturbation. So if you want to have a Lisa binary or a LIGO binary inside one of these objects, you can, if the scalar field that composes the background has a small mass. And you will find a system of perturbation equation for the Schrödinger-Poisson. If instead you decide that your scalar field, your perturber source is scalar field perturbation that are non-relativistic, you will find a different Schrödinger-Poisson system in which some terms basically cancel in one case or in the other. Because as you imagine, you have the energy for the scalar field, that is somehow the mass, the rest mass of the scalar and the momentum. In one case, the momentum is winning. In the other case, the rest mass is winning, depending if you're not relativistic or relativistic. So we have to be careful because the background is perturbative. So the perturbation needs to actually follow the background or be far away from the background, so ultra-relativistic. And that's something that we take care. And in general, it's covered there. So I don't remember by heart what was there, but the idea is that if you wanna arrive to this system is written for non-relativistic fluctuation. So your perturber is something like S2, the star that rotates around the Sagittarius A star. Thank you very much. So the frequency of the perturbation is going to be smaller than the mass of the scalar field. So actually for S2, things are close to mu. So you need to source perturbation that are either way bigger than mu or way smaller than mu. At mu, the equations are very complicated. So I don't know if you can actually write them in this simple way. And also they are not very simple as you see as a matrix, but it might be even more complicated, and it's something that we didn't do. But perhaps is worth to look at also for the results that I will show you next time. That is, the scalar field works as a superfluid. So everything, there is a kind of viscous effect, and the scalar is excited more when the perturbation have a frequency that is close to mu. So the more you're close to mu, the more something happens. It's like perturbers that are very fast, like a LIGO binary inside the scalar field, will decouple from the environment. So nothing really happens there as the end point of this lecture. Nothing. Something can happen, but you have to tune the parameter. So probably looking at this regime where omega is close to mu might be more observatively fruitful, but it's way more complicated. So we are not going to look into that case during these lectures. What we want to do is solving for sourceless perturbation and source perturbation. For sourceless, I mean that I take this system, I don't put any source, and what I'm going to do basically is a deformation of the object with no external physics origin. And that's the way in which you do normally quasi-Neumann modes, in which you want to find the proper oscillation mode of the object. You take your background, you squeeze it, you perturb it, but without a particle that is doing the game for you. And what you're going to find is the only frequency that allow for this system, for this equation, actually system of equation, to be equal to 0. And that happens only if you find the correct Z1 and Z2 with the proper boundary conditions. That's basically how to find quasi-Neumann modes. That's a sourceless perturbation. Then you can do source perturbation. So here you decide your P, which kind of form it has. And inside the source perturbation, there are two kinds, the static and the dynamics. So if I place a black hole in the center of this halo, I'm inducing static perturbation because the black hole is not moving. Or perhaps it's accreting some matter, but it's still not inducing a different than omega equal to 0 perturbation. While if a binary or you have a plunging, then in that case you have dynamical perturbation. That will be the subject of the last lecture. Today, if I make it on time, we're going to look sourced perturbation and sourceless, but the static one for the source case. As you might do to solve the Zerilli equation for quasi-Neumann modes or other kind of system in this game, what you're going to look at is the solution for the homogeneous at 0 and at infinity with some kind of boundary condition that you can control and they're suitable for your system. So in general, what you look at is some kind of regular solution at the horizon if you want to, or at 0, as in this case, if you want to find bound states. And outgoing waves and infinity, or ingoing waves and at the horizon, if you're looking for a black hole, and you're imposing this so-called Sommerfeld radiation condition that tells you basically that the group velocity of the wave is actually going away or is actually entering at the horizon. For our game, we have a star, we impose regularity at the center, we impose wave going away, and that's going to be the two kind of vector we are searching for. Actually, that we impose these boundary conditions, and you find the solution for your homogeneous problem. These K1 and K2 are the exponential that are basically telling you that the Sommerfeld boundary condition, the Sommerfeld condition is being employed. One way of solving this equation is the following. You first search for the solution of the homogeneous problem with the boundary condition that you impose, and then you apply the usual, how it's called? The variation of parameter method that we study in calculus, perhaps 1. In this case, you have a matrix, you have a vector instead of one function, so things are slightly more complicated, but the game is the same. The solution of the source problem is going to be the sum of the integral of the product of the homogeneous solution times the perturbation. So you are integrating your perturber with some of the homogeneous solution, and the other one are outside of the integral, and vice versa. In this way, you will ensure boundary conditions. So you ensure that if you want a regularity at the horizon, this integral is going to 0 because r at the horizon is 0, so this integral is not there, and you impose that this f1n contains solution at a regular at the horizon. At infinity, this is going to 0 because the integration is shrinking, and this guy is the one that is giving you that you have outgoing waves at infinity. This is for the sourced problem. For the sourceless problem, it's normally a matching. It's a matching game when you do the quasi-Riemann modes of a Schwarzschild black hole. Here, things are slightly more complicated because we cannot really match 6 functions with a boundary condition at the center and at infinity. So we employ something that is slightly different. That is, we search for points, for frequencies, for which this F is called fundamental matrix that contains all the vector with all the solution that we found for the homogeneous problem. We search for which values of the frequency this determinant is equal to 0. This will tell us if there is a quasi-Riemann modes or no. And the reason is that the only frequency for which that's true is the one for which solution that are regular at 0 and solution that are outgoing wave, they actually matches. There will be only one frequency for which this happen. So the only thing is that for a one-dimensional problem, it's easier to just employ the matching problem, the matching method. In this case, it's more complicated, but you can show that this is actually happening. And this fundamental matrix is also constant with R. So it's when it's 0 for every R, and because you found the solution, also called the quasi-Riemann modes for frequencies. I perhaps already mentioned the fact that this is a perturbative problem, and normally it's easy to treat perturbations because you can always relate the perturbative quantities, so your delta psi, delta u, with the mass of the perturber. And then you can scale the perturber always smaller, almost 0, so you can ensure that your perturbative method is working. Here you cannot really impose that your mass of the perturber is exactly 0 plus the smallest epsilon you can imagine, because otherwise you should have considered a positron and order in the background. So to be sure that our method is correct, we need to impose that the mass of the perturber is larger than 10 to the 4 solar masses. This is still, you can still capture a lot of things because there are a lot of big black holes inside galaxies, but might be a problem for stellar mass black hole. Well, if you look at the entire Schrödinger-Poisson perturbative system, these terms are almost static. So the dynamical problem that you want to solve for, so the binary, you are expecting that these extra terms that you should account for if the mass is very small, they are actually very much subdominant in the dynamics. So we take them as at least an order of magnitude in the dynamics should be okay, even if the mass are smaller. But for the static perturbation, a black hole in the center, this system is precisely what you want to look for. Let me put this all here. So now imagine that you solved your problem. So you found your delta phi. You can calculate how much is the perturbative stress energy tensor. So the stress energy tensor, the energy of the perturbation, because you found your delta phi, and you can write far away your delta t in this way. Why you wanna compute the stress energy tensor of the perturbation? Because the fluxes of energy, the energy emitted that I was mentioning at the beginning, is actually the integral and far away of the perturbative stress energy tensor. Here is, since I'm looking at the energy, it's contracted with the time-like killing vector. And you can play your calculation. If you remember that the answers for the scalar field as Z1 and Z2 with the two harmonic time dependence, one with plus, one with minus, what you can actually do, it's not a complicated calculation. The only problem is that the expressions are big, so every time you're writing them down and you're putting the integral outside, you need to be careful with the signs, but I mean, every time you have to do that, just these are big expressions, and in the end you can write your E dot radiated as an integral over between this product of the frequencies and the function that you solve for in your perturbative scheme. For a process that is happening in a finite amount of time, so when you look for it, but actually you can write something similar for binaries, but the equation is slightly different. What is going to happen is that you can relate the energy, the variation of energy that the boson star has, that your scalar field has, because of the dynamics that is happening inside. You can relate it with the variation on the number of particles. So how many particles you sent away? Well, you can relate it with the energy lost by your medium, and that is going to be important next time for dynamical friction estimate. And that's why, and that's precisely why, because when you want to look at the energy lost by a perturber, you will have an energy, a momentum, and the linear and angular momentum lost by the black hole that is moving in the medium. But in the meantime, by conservation of energy, some energy is going inside the medium here, delta E, delta P, and delta L. So to compute the energy lost by a perturber, you should know how much heat you gave to the environment. And normally this includes second order calculation. And you don't want to enter in second order calculation almost anywhere in life, and in here especially. But there is one thing that helps us for the Newtonian boson star case specifically, and not for the Q-ball. For the Q-ball case, this is not true. Your U1 invariant action implies no other current conserved, and this implies that you can write the variation of number of particles as minus the particle that were exactly radiated. And this helps you because now what you can do is relate the variation in the mass of the boson star with the number of particles emitted. So you can actually control this delta E. Why you control it? Because now you can write it in terms, because delta E is proportional to delta M, you can write in terms of radiated quantities. So here on the right-hand side, you will have everything it's your code to give you. Your calculator will give you everything that was emitted. So now you can say, yeah, the energy of the black hole that is moving through, or the energy of the binary that is circulating inside your halo, is going to be just a function of things that I can compute dynamically with your radiation. And that's thanks, and the key point of this is that no particles are created. When the black hole moves, depletes the particle, sends away some piece of the scalar, but is not creating anything new. For the Q-ball, the fact that you have that kind of potential doesn't help in conserving the number of particles, and therefore it's more, you cannot really employ this method. On the other side, cuboids are more a proxy for a scalar field interaction. We were studying cuboid for 2 months. We had the machinery going, and then we realized, oh, we could publish the cuboid. And then we were like, but we have the machinery. Why we are doing cuboids? Can't we do Newtonian boson stars? I mean, the machinery is done. And then we basically took the cuboids and put them in appendix, because that was somehow a proxy for a dark matter candidate, while cuboids are not. Here is a summary of what you can do once you employ your perturbative method. You can look for sourceless perturbation, quasi-normal modes. In this case, small spoiler, they will be only normal, but Caio found the quasi-normal, and we checked, and they basically match in some extrapolating limit of a compact object goes to a non-compact object. You can look at source perturbation, so you can put a black hole in the center, or you can look at dynamics. The dynamics is going to be next time. I just want to make a point here. Why static perturbation might be important? But, well, black holes lurk at the center of galaxies. We have images now, Sagittarius A star, M87 star. So what happens if the black hole is in an environment? Is it accreting matter? Is it destroying everything? How fast the matter is accreted by the black hole? Which is the typical lifetime of this double system? Because we already heard various times that this scalar field, there is an O'Hare theorem, so you don't have, for a static black hole with this kind of scalar field around, a solution that is in equilibrium between the back reaction of the scalar and the central static black holes. You need rotation to stabilize the system. So eventually, putting a black hole inside a dark matter halo will have a lifetime, but it will be an unstable system. So which is its lifetime? If you want to look at the typical modes of oscillation of this boson star, so we squeeze the boson star, and we look at the frequency that gives you the determinant of the fundamental matrix of the homogeneous system is equal to 0. You can find all these nice numbers. This number tells you what? First, our machinery is correct, because we control these numbers with, I think, Guzman paper, and these numbers were already known, or either only the first or the first 3, I don't remember, but only this. And then what we found is that these modes piles up towards the values of gamma. Gamma is what I told you at the beginning was omega capital, the mass minus gamma. Well, this has to be way smaller than the mass of the scalar field. And this is related with the potential well of the dark matter halo. And all the modes, you can perhaps see it, they are basically piling up, but after a while we don't have resolution, so we don't really know if they are infinite or they are actually a finite number of them. But perhaps more importantly, none of them has an imaginary part. So once you perturb a Newtonian boson stars, the modes will be this kind of matter modes inside the object, but they will never leak. So an observer at infinity will not measure them. If you add as an ingredient that is very important, the fact that the spacetime might be way more curved than this, so you look at boson stars as dark matter black hole mimickers, there is an extra channel that is basically these gravitational waves, so when you perturb them, you will see that these modes will get a complex part that is due to the fact that now the spacetime is way more curved. In this case, it's not. But we matched that the real part, we saw that the real part were matching Caio's results in a private communication. And well, perhaps this is the last thing that I want to tell you today. Now we place a black hole in the center. And you already know from probably your knowledge before and my talk of last time that WIMPs, so n-body simulation, will tell you that dark matter should be like a spike. So the density of dark matter when it goes towards the center of the halo increases. And if this happens, I don't remember all the details, but if this happens, you might have an annihilation between dark matter particles, because if they are a lot, they interact between themselves, they could emit light. We are not actually seeing that light, and that's also a constraint on the fact that the dark matter halo should not be a cusp. This for Wim's model. In this case, the center of dark matter halo is a core. It's a smooth core. It's not, density is not increasing. But one may wonder, well, black holes are in the center of galaxies. Maybe it's because there is a black hole inside the center of a galaxy that is saying to the dark matter halo, come to me, gets bigger than what it should be alone. That might be a reason for having the dark matter halo as a cusp. Well, so we said, okay, let's put a black hole in the center of our model, solve for the perturbation, and see if there is a huge increase in the density of dark matter. And the answer is no, because the density, the perturbation induced by the external object, that now is a black hole in the center, versus the density of the typical density of dark matter halo in this model in the center, is just 10 times the mass of the perturber over the mass of the boson stars. But as I was telling you before, we are in the approximation in which the size of the object, the size of the boson star is way bigger than the size of the black hole. So the mass of this object is normally, we are taking mass ratio between the mass of the black hole and the mass of the boson star of 10 to the minus 4, minus 5. So this guy is very small. So this increase in the dark matter halo doesn't really justify why people that look at massive particle candidates for dark matter finds what they find in numerical simulation. We find something that is probably more similar to what seems from the observations of annihilation of dark matter particles. No, this I'll tell you next time. I will take more time, so we can next time. Perhaps we are gonna look at only this. That is gonna be something related to what Caio told you yesterday. We have a black hole in the center now, and we allow the system for losing energy. So the scalar field oscillate. You know, the scalar field is oscillating in time. It is on the horizon of the black hole, and we try to answer the question: how much scalar is absorbed by the black hole? How much is the lifetime of this? Because if it happens in a zero, what happens is that your dark matter halo will just go all inside the black hole, and you don't never have dark matter halos. Or you cannot have a black hole inside the dark matter halos, otherwise it eats everything. But as it will turn out next time, black holes are kind of on a diet, so they can eat that dark matter halo, but it takes forever. So it's a kind of stable system. Then if you add rotation, as Carlos and Eugene teach us, the system is even more stable because you can have a back reaction. So your scalar field around might start to co-rotate with the black hole and do an equilibrium system. But this is going to be for next time. And thank you so much for the attention.
Okay, thank you very much, Lorenzo. Are there any questions? We have time perhaps for one question online and one in the audience. Are there any questions online? It's too late. So are there any questions here? Okay, I see 2 questions. I think we have time for both. So
thank you very much for your talk. Actually, can you show the table with the frequencies associated with the quasi-normal modes? So. Yes, my question is, when you consider the L equals 0 and go to the L equals 1, the frequency increases, right? But then when you consider the L equals 2, the frequency decreases.
What do you mean decrease? Decreasing, no? You mean that between these and these?
Yes, yes. Yes.
What perhaps I can tell you, because I think we had the L equals 6, but now I don't remember actually the values for the others. In this kind of problems, for instance, when you look at when you want to calculate the energy, the total energy by the perturber, in this case there is no perturber, you're right. But what you can see normally is a exponential convergence in L. So even when you're gonna solve for the problem with the perturbation, I'm gonna look at I'm gonna prove, but I'm gonna look at the first 2, 3, 4 L, and then extract a potential law, an exponential law. So I don't remember the others, but it might be that this is actually decreasing the value with L. But I should check the values of the table for this precise case that you were asking.
Okay, so thank you.
Okay, Nuno, you had a question, right?
Okay, so thank you, Lorenzo, for your talk. So you said at some point that the mass of the Newtonian star equals the mass of the particle times the number of particles, right? Doesn't that mean that the system or the object is marginally bound? I mean, if you perturb it, it should disperse, right?
Why?
Well, because the binding energy is 0. So I guess that you need to include the next order term in the perturbation in order to get the negative binding energy so that you get a stable system, I would say.
Might be. Right?
So if you look at the phase diagram of boson stars, so if you plot the mass and the number of particles, the Noether charge, you'll see that the first branch, branching off from the Minkowski limit, is stable because the binding energy is negative.
Well, that's
so
something that you expect
guess
from bounded systems, right? Yeah.
Okay.
But it's, I mean, I understand what you are saying. I didn't check the binding energy for these guys. I mean, if you say that because of that is 0, I totally trusted your statement. The only thing is that wouldn't mean that when I'm adding a perturbation that would come out as a stable modes. I'm thinking with
sure,
you
yeah.
right now.
Yeah.
I don't have a precise answer.
As stable modes, not sure.
Because we only find normal modes. So the question would be why, if I perturb a system that is marginally stable, it doesn't starts to be unstable. I don't know, but we can talk about it later.
We can discuss afterward. Thank you.
Okay. Thank you, Nuno. Okay, a fast one.
Yeah, very fast. So I was thinking about so you mentioned very briefly the oscillaton problem. Maybe the oscillaton is a bit, has some characteristics that would, make a huge impact in your computations, mostly because the potential would also oscillate in time. Because you don't only have a scalar field that is oscillating, you have that in the case of oscillaton, your metric is also oscillating. So this introduces like a briefing frequency, right? That maybe if you put some motion inside, this frequency would change the motion at some scales, and you shouldn't even be able to put something at rest, because if you put something at rest and the metric is oscillating, it will immediately start to move. Just a small comment, because...
but is this frequency related, comparable with the mass of the scalar?
Yes, it is.
So perhaps that...
It's very small, maybe. Yeah.
Perhaps for perturbers like S2, it might be very important, but for LIGO, Lizard binary will not.
Yeah, maybe.
I suspect.
Okay, thank you very much. Let's thank the speaker again.